mornings come, you watch the red sunrise. The LED still flickers in your eyes.
So we have 2x dx plus 4y cubed dy is equal to 0. So when we have an exact equation, that means that our p of x, so p is equal to partial f partial x. Okay, whatever our f of x is. We're trying to get to this point here where we can actually find a formula for our f of x and y, and then we'll have our solution. Okay, so in order for this to be true, we have df dx, okay, or del f del x is equal to p, which is equal to 2x in this case, right? So what we want to do is integrate with respect to x on both sides in order to find what's called a candidate function for f of x, okay? So when we do this, the dx's kind of cancel out, and we get f of x and y is equal to, and we have x squared plus, and instead of just a constant c, like a numerical constant, we could actually have an entire function, and I'll just write phi, or phi, of y, right? Of the variable y. Because as you see, if we take the partial derivative of this entire thing with respect to x, this whole term there will go away anyways, because it does not contain any x's in it. It only has y's. So that's why that's why we have this extra function here, just in case. Okay. So once we get to this point, we kind of stop. We've reached a point where we can't continue and we can't just guess anymore. Okay. So what we're gonna do now is work the other side, and by other side I mean q is equal to partial f partial y. Right? That's what it means to be exact as well. So we're just going to rewrite this on this side here. So partial f partial y is equal to q, which is equal to 4y cubed. So now we're going to integrate with respect to y this time, okay? Integrate with respect to y. So we get another candidate function, which is f of xy is equal to y to the fourth. And this time we could have like a function of x, which goes away when you take the partial with respect to y. Okay, so now we have this other candidate function, and what we have to do is these things have to be equal to each other. We want the same one. We want to end up in the same exact place, right? So what we do now is we just set equal everything that we see on both right sides of our equations. Okay, so this is going to be x squared plus phi of y is equal to y to the fourth plus, and this is psi of x, I believe, something like that. So once we have this, we can just see that, okay, our single variable function of x should be an x squared in order to equal the one on the left, right? So this should be equal to x squared, as should this function be equal to y to the fourth. So that means that our this thing is equal to y to the fourth, and this thing is equal to x squared. So we end up with one function, which I'll write on the next slide. So our one function, our final function, is going to be equal to x squared plus y to the fourth, and then we could just set it equal to a random constant c. Okay, this is usually how the answers are formatted here, our solution to the ODE, our exact differential equation. Okay, so now the big question is, all right, so we said if partial p partial y is equal to partial q partial x, then that means our equation is exact, and we just solve as I just showed you on the previous problem. Okay, we approach it from two different sides. We find the potential functions, two potential functions, and we try to match them up to get that one single function at the end. Okay, so then our equation is exact, and we just solve like normal. Okay, if not, so then we have this other case. So if partial p partial y is not equal to partial q partial x, then we have to try to make the equation exact. The equation exact, okay? And how are we going to do this? I'll show you a variety of different ways, starting on the next slide, okay? So the first kind of equation that we could have where it's not exact is what's called a separable equation. Separable equation, and this isn't anything different than we've already learned. So separable equations, it's kind of like I'd rather just separate and integrate kind of thing. So that's what we'll do for these kinds, and we've already learned this, so I won't go into too much detail about this. So we're just going to separate and integrate and solve for our function here. Okay. Another type that we could have is a linear equation, which again we've already visited, so I won't go into too much detail here. So linear equation, for those, we have something that looks like y prime is equal to a of x times y plus f of x or something like that. Okay. Then you just find our integrating factor here, which would be a u of x in this case, which is equal to e to the negative integral of ax dx, okay? And then you just multiply that on both sides, so we get mu times y prime minus a times y is equal to mu f. This is equal to the following, okay? And then you just integrate on both sides, integrate with respect to x, that is, with respect to x. We just get mu y is equal to integral of u and mu f, which are both functions of x, and then so plus some c. So y of x ends up being 1 over mu, which is a function of x, times the integral of all of these things, and I'll just stick in the x's where they should belong, right, plus c here. And that would be our answer here. So that was just a very brief run through of how to solve a linear equation, okay? So that's that, and now we'll get on to the new stuff. So another type of equation that we could run into is when it's neither separable nor linear nor exact, okay? So then this is where it comes into play. Remember that those other two equations that we run into that I showed you how to derive and everything. So this was when we had our partial f partial x is equal to some mu times p, and we also have that partial f partial y is equal to some mu times q. Okay, and I said that, well, mu, this could be a multivariable function or it could be a single variable function. So it could be this, or it could be a mu just of x, or it could just be a mu of y. Okay, and these are all called integrating factors. Integrating, or integration, or you could say integration factors, okay? And these are pretty useful. It's kind of, I don't know, I think it's kind of fun to try to figure out what they are, because it's like trying to find a piece of a puzzle, like a tool that will help you solve the rest of the problem, right? So that's basically what they are. Whatever they are, sometimes they'll be multivariable, but we won't go over those. If anything, in the book, I believe, in the practice problems part, they can give you, if your integrating factor is a multivariable function, then they provide it for you, okay? You don't have to find it. But in this section, what we're going to do is find if we're told that our integrating factor is only a single variable function, it'll either be a single variable function of x or a single variable function of y, okay? And then we'll learn how to tackle that. Okay, so when we have something like this, then we're going to kind of utilize Clairaut's theorem, right? So let's say our Clairaut's theorem, remember that's when we have the partial with respect to y of whatever our p is, but in this sense, now we're going to have mu times p, okay? Because p by itself, let's say, okay, so let me back up really quickly. Let me just show you where I'm coming from. So when we have the case where our original p and our original q do not satisfy this, when this does not happen, when this equality is not there, then that means our equation is not exact, right? So we need the help of an integrating factor of some sort. One of these here, okay? And we don't know what those are, but we do know that when you multiply by that integrating factor, okay, when we multiply both p and our q by those integrating factors, then we do have that equality where we can take the partial with respect to y of whatever p is times that integrating factor is equal to the partial with respect to x of our mu times q. Okay, then, so when we, again, just to review, when this equality is not true, when our equation is not exact, as it is, then we're going to find an integrating factor, mu, either of one or two variables, and then when we multiply both of these quantities by that mu, then this equality does hold true, and we have an exact equation, okay? Alrighty, so when we have this, and our exact equation, by the way, will look like this. Mu times p dx plus mu times q dy is equal to 0. Then this equation is definitely exact. Alright, so let's take this here, which I'm boxing right now. We're going to take this and expand off of it on the next slide. Alrighty, so let's say I have this equation up here. Okay, so just keep this in mind. We'll be working with it plenty in the following slides here. Okay, so the first one, like I said, if they have, if your integrating factor is of two variables, is a multivariable function, then they'll give it to you in the problem, okay? If not, we have a single variable function of x or a single variable function of y for our integrating factor. So let's do this one first, and then we'll work on this one, okay? So the first one is if our mu of x is only a single variable function, so it only depends on x. If this is the case, so if this, then we have that this thing here, okay, then the left side, this thing is only a function of x, so that means it'll just kind of stay there. It'll hang out while we do the chain, well, sorry, not the chain rule, but the product rule, while we take the partial derivative of p, and if we were to do partial u, partial y, this is going to go to 0, right, because it doesn't depend on, it doesn't have any y's in it, so this term is going to go to 0 completely. But on the right side, we do have a product rule thing going on, where we have something like this, plus mu times the partial of q with respect to x as well. Okay, so here, again, this term here goes to 0, so I'm just going to black that out there. So then we can actually devise our own, like, new kind of differential equation. So del mu del x, I'm just going to solve for that. This is going to equal, if we get this by itself, we're basically going to get 1 over q times del p del y minus del q del x, and del means partial, right? So we have something like this equation here. All right, so when we get to this point, we actually have, this turns into somewhat of a separable equation, okay? And we can just solve for mu, okay? And we'll get our mu of x, and I'll do an example of this. This is just talking theoretically about the process, okay? So then we'll get our mu of x, okay? And then once we get that, we're going to multiply. So we're going to find this guy. We're going to multiply our entire equation, our ODE, by this mu of x, because it's our integrating factor, right? And then our equation, well, we could say to make it exact, all right? Make it exact, because once we multiply by our integrating factor, our integration factor, then our equation becomes exact, and then we just solve like normal, okay?